Yes, thank you. So sorry for the short delay. We still have technical trouble, I guess, but now everyone who's online should be able to see through the camera of the D10 system our speaker, Marius Lindauer. So I've known Marius for quite some time now. He did his PhD in Potsdam, was a postdoc and I believe junior research leader, right, in Freiburg with Frank Kutter. And together, I'd say they've built up a AutoML empire of really great techniques, right? I think so. And have definitely become central figures, I think, in this field. So we're very happy. And so then Marius got a professorship at the University of Hanover. And so we're very happy to have Marius here to tell us a little bit about AutoML and some of the new techniques. And also, I'm very excited to see how to make it explainable. So thank you very much, and we're looking forward to your talk.
Thank you very much for this kind introduction. So I hope that everyone can hear me also online. If not, simply start complaining. I can see it on a bit if I look into the right. Always the chat a bit. So today I would like to talk about is actually what is really to my heart. That's automated machine learning. And I don't only want to talk about automated machine learning, but efficient and explainable automated machine learning. So I guess you all know, and that's maybe one of the reasons why you're sitting here, that you all somehow believe in the success of AI. There are many major breakthroughs in AI in recent years, many very successful applications in all kinds of fields, be it in chemistry, medicine, intelligent production, logistics, and many, many more, even in arts, right? So many applications out there, and more people working in AI, actually. Nevertheless, really, I don't know whether you all already experienced what it means to really develop a new AI application, right? What it means these days, if you're talking about AI, it means somehow machine learning or even deep learning. Of course, that's only one part of AI, but I think that's the most central part right now. So if you would like now to apply machine learning to a new task, whatever you prefer, actually, you have to consider three things, right? First of all, you need your hardware. Without a big GPU, it's fairly hard these days to really achieve something impressive. Secondly, you need your data. So you need somehow good data, created clean data, and from many sources. So many people also talk about the part of data. What I'm most interested in is the third part, actually, which is then the machine learning. So how do we process actually our data in the way that we get a prediction at the very end? And if you're doing that now on your own, we have a very common workflow, which more or less starts with an expert defining the task. Then someone is sitting there and trying to collect some kind of data and different kind of ways you can do that. And then you have to define what I call the machine learning pipeline. The machine learning pipeline really consists of data cleaning, feature engineering, model training, and maybe even some kind of post-processing. For all of these components, actually, you have different kind of algorithms how to do that. All these algorithms maybe even have some hyperparameters you have to play with. And only the best combination of all of them will give you really state-of-the-art performance, which you can later on redeploy. So that's the goal, right? And what simply happens, you need some kind of experts being knowledgeable in all of these kind of parts, trying to figure out really what the best combination is. And unfortunately, that kind of a task to figure out the best combination is very tedious, it's error-prone, and it's time-consuming. So people sitting there maybe for weeks, months, or even longer to figure out what a good machine learning pipeline is, after they invested maybe already half a year in collecting data. That's the reason why our goal is really to support developers in automating this part. So what we're trying to build is AutoML tools, which simply propose machine learning pipelines giving you data. So our overall mission is to enable users to efficiently apply machine learning for some new kind of data sets. So if I'm talking about these kind of design sets of these kind of machine learning pipelines, what we all take into account, give you some examples, we can see that and read that. So of course we have the predictive algorithm. Let's talk about classification algorithms, for example. If you're looking into literature, you see that there are actually more than 100 different kind of classification algorithms. Which one should you pick? most often what happens, you simply pick your favorite one without really having any justification for doing that. And all of these actually have hyperparameters again. So maybe you can see that column over here, which indicates how many hyperparameters all of these have. So for example, if you're really going to SGD, a linear classification model, which is a very simple approach, but it has 10 hyperparameters you can actually choose from. If you even go into the direction of deep learning, what happens is we have to talk about the architecture of the deep neural network. How many layers, how many neurons, how many channels, what kind of operators, what kind of connections actually between the different kind of operators. So you have a whole bunch again of design decisions. And it really depends on your deep neural network architecture, whether it performs well or not. You can talk about preprocessing. There are a lot of many preprocessing techniques out there, like the classic one, a PCA already. And even if you're only talking about the PCA, we have again 7 hyperparameters you can play with. And maybe you don't want to have only one preprocessing technique, but several of these. You would like to have really pipeline of these, right? That's really only PCA. So, and you can actually extend the list and can go longer and longer, and actually with system really take care of more than 100 of these design decisions. Now we will say maybe, is it really important to do that? Can't I simply, I don't know, use my XGBoost or my standard deep neural network on it and everything's fine? And here that's very old picture I'm using, actually I have to admit, for the last 5 years. It's always the same picture, but I think it makes my point very clear. So what we simply did is on very specific data set actually, and it's actually one of these very easy data sets even. We started to look into different kind of classification algorithms like gradient boosting, kernel SVMs, random forests. What we can always see here, if we're talking about balanced error rate on the y-axis, that choosing correct algorithm gives you already an absolute improvement of 70% in error rate. So SVM is not performing well at all. Using default settings, the gradient boosting is performing quite well. And then what we can simply do is someone sitting there trying different kind of machining pipelines, playing with all these hyperparameters being involved. And more what you see here on the graph, all these little kind of dots are one other kind of machining pipeline. And hopefully over time you will find better and better ones. So these curves should go down. Of course, from time to time, maybe it also jumps up because it's not, was not a better one. But after investing quite some time, being it you as a developer or being it's machine finding that, what we can see here is with the optimized pipelines and the corresponding hyperparameters gives you another 20 to 29 absolute improvement. That really means we're starting from random predictions for the very poorly performing SVM, going down on the data set to state-of-the-art performance. So it really matters to use some kind of techniques to figure out what is a good machine learning pipeline. So hopefully I convinced you by now the overall motivation of automated machine learning. So that was more as an introduction. Now let's talk about more the cool stuff, right? And I would like to talk about a paper which will be published at NeurIPS, which is the biggest machine learning conference actually in the world. Very soonish actually in December, so it's NeurIPS 2021. And for that paper, we actually considered one very particular problem, actually how well can deep neural networks perform on tabular data. Okay. So if we talk about tabular data, there was so far actually the belief that deep neural networks are especially well performing on high dimensional data modalities. So most of the times if we think about deep learning or deep neural networks, we think about images or text actually, right? That's what many people actually use deep neural networks for. But if you think about tabular data, the state of the art is considered using some kind of gradient boosted decision trees, XGBoost or variants of that actually. So that means really like really more traditional way, building trees, stacking these, optimizing some residuals of that, and so on. So that's more as what many people are using. Also, if you're looking at packet composition and so on, that's more really considered what has to be used. And we were thinking, why not deep learning? Why is that not possible to apply deep neural networks to these kind of data? So what is missing actually? And we were thinking, yeah, deep neural networks are over-parameterized. So we have many parameters, many weights of our deep neural networks. And actually the tabular data often have a much smaller dimensionality than images or text. So maybe there's some kind of relation to that. So maybe what we're simply missing is a good regularization technique, right? So regularization prevents overfitting. Maybe we only have to find what means regularization for tabular data. So we're starting to look into the literature and figuring out a lot of stuff, actually. That's this very, very long list of fancy buzzwords. So, of course, you can go back into the 90s. You have something like rate decay. You maybe have that in 2014, dropout, very famous, right? Batch norms, skip connections, and so on, shake, cut out. There are many actually famous of these regularization techniques. However, these were not designed for tabular data, right? These were designed mostly actually for image data. And we were thinking, why not applying these to tabular data? Let's try that. So what we did is actually now saying, yes, we can apply all of them. Why only one? Maybe we can need a combination of them. All of them have, again, hyperparameters. We can choose, making the regularization maybe a bit stronger or different in how we can apply them. So actually what we did is building a huge configuration space of possible regularization cocktails, what we call so simply combining several regularization techniques we call a cocktail. And of course, we have to find the best cocktail doing that. How can we do that? So of course, now the answer should be clear to you since I'm an automated machine learning guy. You would like to apply automated machine learning to that. Why is that not so trivial actually in the first place? First of all, training a deep neural network is fairly expensive, right? Luckily, on the tabular data, it's not crazy expensive. You can still manage to get some of these, but it's not like you can afford 10,000 different kind of trainings. So we have to be efficient, actually. Secondly, we're really talking about a pipeline of regularization techniques, which is then our cocktail, but it's not only talking about one. And on top of that, each of these regularization techniques maybe has some own hyperparameters. So we have a structured space we have to search it. As a background, what are the typical automated machine learning techniques? I think the most famous one, actually, community is Bayesian optimization. The idea is we don't know what is the relationship between hyperparameters and the loss or the cost we'd like to minimize. We don't know that, right? But what we can do is simply train our deep neural network, giving some kind of hyperparameters, and observe what is actually the loss we would like to minimize. So we can query actually our unknown function. And since we can query that, that means we can get some kind of data, and data means we can fit a regression model on that, right? And what Bayesian optimization is doing on top is not using simply a regression model, but a probabilistic one. So we get some kind of uncertainty for each of the points. And that helps us there to trade off exploration, exploitation, where we can maybe focus more on parts where we are very uncertain actually what is the true loss. Or we can try to exploit in the regions where we believe there should be best hyperparameter configuration. And that really means we have a global optimization strategy. It's very sample efficient because we can do a lot of things on these kind of regression models we fitting. And normally it's considered to be very efficient for small and medium configuration spaces. Of course, we can go also in another direction, and that could be evolutionary algorithms. And here simply saying that each population member is one of our hyperparameter configurations, or here in the specific case, one of the regularization cocktails. We can, of course, apply mutation, cross-over selection. I think Kevin is a much better expert in that part than I am. But the nice thing is that population-based approach. So that means also that we have many functional variations. So many times you can really train our deep neural network and get some kind of loss base so that then EAs are a very good fit actually for that. On top of that, it's easy to parallelize. So if you have many GPUs, actually quite nice, apply an EA. Next, what is also known as reinforcement learning, which is very famous if you're talking, for example, to optimizing the architecture of a deep neural network. You can see that actually as a reinforcement learning problem where an agent picks what kind of architecture you should choose. Then the environment, so your deep neural network, is actually returning how well it performed and how the training was actually going. And then the agent will learn based on that feedback how to perform next. That's a very human-like approach, right? That's what maybe as you would also do that, you would try things out, get some feedback, try again, things out. I was learning some kind of a policy that can even maybe generalize to different kind of data sets, which is somewhat nice, but I have to admit, it's not my favorite approach simply because it's not efficient. So Spatial optimization and evolutionary algorithms for automated machine learning are often much more efficient, in my experience. What you can also do, and I mostly mention that because maybe people from Paderborn are also part of the meeting, is planning. So there's also planning approaches. Actually, you can try to plan what kind of a pipeline you would like to construct. So what we were actually using is really Bayesian optimization, fitting these kind of regression models, training of exploration, exploitation, and then adding something on top, which is hyperband. The idea of hyperband is very human-like. So imagine you training a deep neural network, and that maybe takes an hour or a day. And then you're starting to really observe your learning curve, right? So that's more as what you can see here. So you have number of epochs on the x-axis, you have your error should go down by training the deep neural network, right? But if you already observe at the very beginning that your deep neural network is not really training well at all, it's not making a lot of progress, you simply will terminate that early on, right? Maybe wait for a few minutes, you see there's nothing happening, stop it. The idea of hyperband is really like the same. Simply saying we have a bunch of deep neural networks, we're starting to train them for a short amount of time, stopping the poorly performing ones, so we terminate already all of these, and then continue only with the better performing ones. Training a bit longer, stopping again the poorly performing ones, training for a bit longer, stopping the poorly performing ones, and in the end, we really invested the most compute time in really the good performing ones. Good. So that approach is then called BOP, combining Bayesian optimization for sampling these kind of configurations. So more as these starting points over here, and then how long we should run all of these, and it's the approach of hyperband in a nutshell. So now coming to results. The first question was, of course, if we're doing that, finding good regularization cocktails by using BOP, can we actually outperform state-of-the-art deep learning architectures on tabular data? What we really did is here using a very simple MLP architecture. So we're not talking about the architecture of the neural network. We're only trying to figure out what is a good regularization technique. What we can see here, and that's the critical difference plot, we were doing that on 40 data sets. So not only one is boring, but on one you can always outperform something else. But really, you're talking about 40 different tabular data sets. We have different kind of competitors, like for example, Node, or we, for example, also tried what happens with an MLP and using kind of different kind of activation functions. Sorry, or TabNet is very famous actually in the community. All of these, and then what you can see here is the average rank across all of these 40 data sets. For example, you see that TabNet with ensembles, on average, it's ranked 7 actually only. And what we actually here propose is the MLP plus C. So C stands for the cocktails. And you can clearly see that on average is the best one. It's not on all data sets the best one. I can't guarantee for that. But on average, it's the very best one. What you can also see in these kind of plots is that some of these lines are actually connected with some kind of stick bar, right? And if it's connected, that means there is no statistical significance actually that these really perform differently. So, but because our cocktails have no connected bar to anything else, which really means there is statistical significance that we are outperforming everyone else. So it's not by chance that we are outperforming, but we really have a lot of evidence doing that. Good. Now we talk only about outperforming deep learning architecture. We will say, yeah, deep learning compared to deep learning, boring. Why? Please give me the beef. And compared to really gradient boosting approaches, right? And here we have the results for doing that. So we have the famous XGBoost, maybe combined with ensembles. We have CatBoost. We have from auto scikit-learn the boosting. We have XGBoost plain. And we can see again, our MLP combined with cocktails performs best, significantly best. Again, not on all data set best, but on average, that's the best performing one. Now, maybe you'll come to the idea and telling me, yeah, it's a big configuration space with many design options. Simply tuning XGBoost should be much more efficient, right? XGBoost, something has, I think, 8 hyperparameters compared to our cocktails. That should be much more efficient, right? It's only fitting trees. Come on, can't be too hard. So time-wise, maybe our cocktails are very nice performance-wise, but maybe not time-wise. Here are the results time-wise. So we invested how much time we invested really for tuning all of these for each data set, and then it's the average rank across all data sets. And we can see that even at the very beginning, a good cocktail helps you already, and by tuning that more and more, there's much more potential you can get out of a cocktail than you can get out of XGBoost, actually. And if you have a diverse set of data sets, you need that kind of potential. So really, at the very end, our MLP plus cocktails is really clearly the best performing one. Good. That was more or less my story about how well automated machine learning can now generate new state-of-the-art performance on tabular data using deep neural networks. But there are some limitations. I have to be honest with you, of course. What we did here in our study was only doing that on classification. We have no clue what happens on regression, which is fairly understudied actually in the deep learning community. And on all of the regularization techniques can be transferred to regression. We also haven't looked into semi-supervised or streaming data. We have no clue about that. We also only concern somewhat well-balanced data sets, so that the class distribution is somehow balanced. We have only used a fairly simple DNN architecture. This was an MLP. So, and there was no general HBO. We have not really configured all of these options. I strongly believe if you would do that, you could get even much better performance. And last but not least, we have also not used the best AutoML tool, actually. So Bob is from 2018. We by now have two SMAC 3 developed by my group. Actually, I know that it's outperforming Bob, actually. So the last 2 points are actually only showing that we haven't really got until the end. I think we can get even better results. Good. So applying automated machine learning, awesome, right? I hope you agree with that. It's working. But now you will maybe say, yeah, but I as a human, I as a data scientist, I as a machine learning practitioner, I don't have a job anymore. What should I do now? That would be very boring, right? With everything now push button technology, everything is fine. So let's talk about humans and automated machine learning. Because if you have these fully automated systems, it can also receive quite some pushback. For example, we don't know why automated machine learning tool returns certain kind of pipelines. We really have no clue, really. That's trying things out and giving us something at the very end. That's not very satisfying as humans, right? It's also not easy to bring in your own expertise. Maybe you already played with deep neural networks. You maybe already have an intuition. What is a good learning rate, maybe, right? And of course, you don't want to start searching from scratch for that. Also, if you are a data scientist, most often what happens is that you have a fast prototyping-driven workflow. So you're trying things out for a few minutes, trying to learn a bit, see what happens, where it fails, and you would like to change something and doing something again. It's not like data scientists are looking for technology where they press a button, wait a week, and then maybe it was a success or failure. So automated machine learning is not guaranteed to work always well, right? Maybe there's bugs somewhere, or maybe the data was not processed correctly, or something that went wrong simply. So waiting for a week can be a waste of time still. That's the reason why I believe, and I try to pitch that idea now for roughly half a year, is that we should go towards human-centered automated machine learning instead of fully automated one. What do I mean with that, actually? Get that annoying thingy now. Okay, nevertheless. So what I'm proposing is actually X automated machine learning, and X stands for first interactive and explainable. How do we do that? So first of all, of course, we have the automated machine learning loop, and that's more or less we select a new pipeline, evaluate the performance on that, and doing again selection. So that's more or less really a fully automated part, the upper part over here. But I believe from time to time we have to bring in the human again. And how do we do that? My idea is saying automated machine learning is also collecting data. It's some kind of metadata. And metadata really means we have different kind of pipelines, and we observe the corresponding performance or loss or whatever you'd like to call it, right? We have some kind of performance measurement for a given pipeline. Using that kind of metadata, we can now start to explain automated machine learning. And we maybe are familiar also with the big field and very prominent field these days of explainable AI. There are different kind of ways actually to start explaining this kind of data. We could use them. So the hope is that we can then derive quantitative and qualitative explanations And now, let's assume that the user will be able to understand what's going on. That will also enable the user to interact with automated machine learning. Interaction could mean maybe update our configuration space, maybe update the constraints involved, maybe some preferences or priors being involved, what we'd like as an outcome, right? If we understand what's happening, we can also talk about what I would like to achieve actually. And that we can feed into the AutoML loop, that can work again, and then we do maybe the outer loop again from time to time. That's the main idea. And I was also having some first success at trying to build that vision. So I think we need the next 5 years to really make that happening, but we have the first steps towards it. And the first step was really, can we start to explain what AutoML figured out? And that's also will be very soon published at NeurIPS 2021. The idea is simply going back to a very easy, explainable machine learning technique. This is called a partial dependence plot. The partial dependence plot is essentially very simple, actually. So let's say we would like to talk about hyperparameters, let's call the hyperparameters vector simply lambda. Let's say the one we are interested in is capital S, right? Which simply means we have an expectation over everything else we don't really care. So what we're actually doing is integrating out all other hyperparameters. So we are only interested in the hyperparameter effect of maybe one of our hyperparameters. Let's say we would like to know, I don't know, what is the effect of learning rate? Or we would like to know what's the effect of changing the batch size. And then you get maybe something like such a plot, where you have on the x-axis your hyperparameters. You can maybe talk about different kind of settings. And then you see how it really reflects to your cost, performance, or whatever you would like to call it, right? You see what the effect is on how well it performs. What it really means mathematically is simply saying we can use Monte Carlo integration. So for all kinds of observation we have, what we're simply doing is have an ice curve. An ice curve simply means we are fixing all hyperparameters, but the one we are interested in, and then simply change that. And how do we change that and get the now prediction is simply, yeah, as in Bayesian optimization, we fit it already in the regression model and all this kind of performance data, right? So we can simply using all observations we had on pipelines, fitting in the regression model, and then simply we can query that for all kinds of hyperparameter settings. So, and then what the PDP is simply if we have these different kind of ice curves, simply an average across all of these. And then we get already a PDP. So PDPs are somewhat nice, but they're lacking one thing, which bugged us actually quite a bit, that they don't have uncertainty estimates, right? So we can see actually from the plot we had on the last slide is that here at the very beginning, the fit was actually fairly nice. And we only know that the fit was nice because we know the current truth. And in practice, you don't know the current truth, right? So the black curve over here is unknown. What you only get is a green curve. That's your estimate. So what would be actually nice to have some kind of uncertainty attached to that, saying, for example, like in that plot, we are very certain that part, and then we have this squarish area, which is telling us we are very uncertain actually over here, right? That would be very nice to have in addition. We can show actually in the paper, I'm making it short a bit here, not going too much into math, that we can also derive these kind of uncertainty estimates if we have a probabilistic model telling us for each point actually how certain we are, and then we need only to think about how to average that correctly. Why do we need that now for automated machine learning actually? So that's a bit tricky. It's not like we can now simply throw it on our data and our surrogate model, as I told you already. It's a bit more tricky. Because what kind of data are we actually collecting in automated machine learning? So first, let's talk about what kind of data we have in machine learning. In machine learning, we simply assume there's some kind of unknown distribution of data we can sample from, and that's somehow fixed, let's say, right? And we simply have some kind of approximation of that. But for automated machine learning, we have a generating approach, actually, and that's the AutoML tool, which says, how do we sample action in our space? What kind of observation do we really get? That there's no underlying distribution you can make use of. And what simply happens is that automated machine learning is, of course, biased towards the well-performing areas. So in that plot, for example, let's assume on the x-axis you have one hyperparameter, on the y-axis you have another hyperparameter. Your color scheme tells you how good you're performing. So if you are here really in these bluish areas, you are performing very good. The optimum actually is over here. What we see here is actually if you have a high sampling bias, and that's desirable, we would like to have that, is that automated machine learning will focus on the good part, because we would like to figure out the good machine learning pipeline. We don't want to waste a lot of points on everything else. We have to explore a bit, but we would like to focus where we believe in the very end that's a good one, right? So if we have a high sampling bias, everything focus here. If we have a medium sampling bias, you can see we have more scattered points, also here a bit more scattered, but still somehow focused. And if you're doing something like random search, actually, we cover the entire space, right? So in practice, what we have is high sampling bias, but of course, we could also go to low sampling bias, but would not make sense for us. What does it mean actually for PDPs? If we're now fitting on these kind of data as a PDP again, if we have low sampling bias, actually our PDP estimate is quite nice, right? Because we cover the space. We know actually what is happening in that kind of space. If we have a medium sampling bias, we have a bit more off. We are far more uncertain. If we have the high sampling bias, we have quite some off from the ground truth, right? That was the black curve. The blue curve is here the estimate. And we are fairly uncertain actually now. So that's really, really bad for us. And of course, we don't want to change now the sampling scheme. We still would like to be biased. So we can't directly use now PDPs on that kind of data. It's nice that we have now the uncertainty estimate. At least we know how certain we are, but still we are fairly uncertain in most cases. As a first step, and I really have to admit it's only a first step, but the idea was saying in some parts of the space, for example, here or here, we have quite some observations. We know some of these points, and maybe our PDP is good. In some other parts of the space, for example, here, we only have this 1 point, 1 observation. Of course, our PDP will suck simply. There's no other way in doing that. We can't avoid that. But we cannot try to split our space. So if we know that at least there are subspaces where we can have good explanation, good PDPs, we can try to figure that out. What it's simply doing is using that kind of uncertainty estimates you already get for the PDP and try to check for different kind of subspaces actually where the uncertainty structure decreases. And that's here on that example. So for example, here we had again the 1 hyperparameter, so it's again 1 PDP. We have the blue curve as the estimate and the grayish area as the uncertainty. And let's say that we're splitting some other hyperparameters and saying that has to be smaller than 6 maybe. Then we're getting already for that one a much better PDP estimate. On the right-hand side, it's the same. It's a bit better, not much better, but it's more as figuring out on that part of the space actually getting much better PDP, which is not unsurprising, right? Because we have most likely also many more points in that space. We can simply do that kind of splitting by using more the idea of decision trees. So we have now a way to define what's the loss function for saying how much the uncertainty structure increase. And then we can simply try to split in a tree and going as deep as we'd like to, or as much as the user would prefer to. Give you some examples from deep learning. So here what we did is, again, many deep learning models actually trained on some kind of data. And there's only one example. For example, we talked about batch size, and that's actually on the log scale. Of course, we don't have a batch size of 4 or 5, so it's always 2 to the power of 4, and so on. And we somehow have here, it's not actually the performance, but actually loss, as we maybe would like to minimize. We see that if you talk about the entire space, and we have here 9 other hyperparameters we integrated out, we are very uncertain, and because we know on that artificial example also the ground truth, we also are not a good fit over here. But we see then later on that if we split already on weight decay, we get better somehow a fit, and if we split on number of layers, weight decay, and max dropout, we get a reasonably good one actually already. So we have to more as we consider subspaces, and if the nice things also of knowing these kind of subspaces and having something like a decision tree which you can interpret is that we know how batch size maybe relates to some other kind of hyperparameters. So batch size has to be obviously in relation to number of layers, weight decay, and max dropout. And the same, of course, you can do with the number of maximum units you have. Very uncertain PDP, splitting on batch size helps you a bit, and then splitting on some more, you get a very good. Good. So now I hope I convinced you that it made the first step towards explaining what automated machine learning figured out. There are a lot of more questions to be answered, but at least we have something. Now the other part was I mentioned before is, what about bringing in your own expertise? Let's assume you already worked in kind of machine learning for the last, I don't know, 5 or 10 years, maybe even you have some intuition, some gut feeling already. how can we make use of that in automated machine learning? And that was, don't forget to mention that was actually a paper which was in this summer published at ECML 2021. So the idea is really the ML practitioner data scientist has some kind of intuition. Maybe here on the axis, some kind of probability distribution, saying it's the user maybe can define it's fairly likely that could be good region, and that's one hypermodal dimension, and that's another hypermodal dimension. Maybe that could be also a good part. So overall, we should maybe sample here a bit more. It could be also here or here a bit, but that part of the space should be fairly unlikely, right? So we should try to bias actually our search again to some kind of subspaces. However, of course, if that would work all the time, then we don't need automated machine learning anymore, right? So if you would have the intuition, that would be always correct, that would be awesome, but we don't have that. So over time, what should also happen is simply that we should not always trust the prior intuition, but if we get more and more evaluations, actually we should trust more what automated machine learning get out. We need some kind of a trade-off over time. How to do that? So now we are going back to Bayesian optimization. Bayesian optimization, as I already mentioned briefly, more what we're doing is trying to estimate an unknown function f. For this unknown function f, we can have some kind of observation. These are these little dots over here. On these observations, we're putting now on the regression model. That's the solid line connecting these kind of dots. And we have some kind of uncertainty estimates when we are far away actually from observation. So being in the middle of that one is actually quite far away. Of course, we have high uncertainty. If we are very close to an observation, we should have low uncertainty, right? And that's what Bayesian optimization is actually making use of. Now, that's a bit not what you like to do, actually. When I go back here, I was saying the user, what the user can define is probability of being good in certain regions. The user very rarely can tell you exactly what is the function value, right? The function value, how good it will be quantitatively, right? So what is the exact loss at the very end? That's very hard. You can't do that. You can't expect from the user. So we have to go back somehow to a definition of being good. We can make use actually of an idea which goes back to TPE and saying simply, okay, we have some kind of observations, and let's simply say that maybe 25% of our observations are the good ones. So the 25 best ones actually are the good ones. And everything else, so 75% of our observations, the poorly performing part is called the bad ones. So most using a quantile on our F, what we observed, which here my 4 observations simply means that that's a good one and everything else is bad ones. If we have that now, we can also say from the model we fitted that's somehow a normal distribution. We always assume that. That's of course not a perfect assumption, but we simply do that to make our life a bit more easier. So that kind of uncertainty we have is the distribution is normal assumption. And simply combining that now with our threshold is simply we have some kind of probability now of being good again, right? So that's part of the probability mass is telling me how good we are. So that's more as now we have a model for each of our configurations telling me how likely it is to be good. And if we then can simply combine that, and that's the prior knowledge from our expert, he or she was also defining what it does mean to be good on the configuration, what's the probability of being that. We can simply multiply that. And the only thing what is now missing is what I told you before, simply saying we would like to trust our model, so our estimate from our observation more over time. We simply did that. So our model actually, we have to the power of t by beta. Beta is some kind of hyperparameter of the method. Simply tell you if you don't want to trust your model too much, but more your own intuition, you should adjust beta or the other way around. So that gives you a bit of way to adjust the method. But over time, of course, the number of t's, the number of evaluations we have will increase. So the emphasis will actually be on the predictive model and not on the prior from the user. So that was the one idea we had, which was published at ECML, as I said. But we figured out it was a bit not the most easiest way to implement, right? So we have to change somehow how we model our data. We have these normal distribution assumptions on it. It's a bit hard somehow to really make that happen. And then we just think, why not make it simpler? And that was the idea which is now under review for IKEA, which is called PyBo. PyBo is much more simpler, actually. And that goes back to the idea that at the very end in Bayesian optimization, we have this kind of predictive model, but we need this kind of trade-off between exploration and exploitation. The simplest way of doing that trade-off is actually called lower confidence bounds. That's the line over here. So we have more as the posterior mean estimate given a point. And so if that should be actually quite low, or quite high, depending on what you have maximum minimize, I say that if that would be quite low, that would actually be a signal for exploitation, right? So we'd like to go more in that direction. We're simply adding now a couple of times our uncertainty estimate. So if the uncertainty, of course, is high, we would like to have more exploration at part. So where we are very uncertain, we should maybe look into that part. That's a very easy way of having an acquisition function. Acquisition functions are normally point alpha in my community. And what we simply can also do is alpha, as well as giving a score on X, so configuration, we simply multiply that by the prior of being good, defined by the user, and simply adding the same trick of having more weighting over time. So it's a very easy way actually to combine these two ways. And so we can combine it with any kind of acquisition function, we can put it into any kind of BO tool. And the nice thing is it still has the same convergence guarantees as we had before. For the approach here with Berkeley, there's no convergence guarantees. If you already have convergence guarantee, that still applies here. Showing you some kind of results also on that actually. So that's on UNet, so on a medical data set, and that's on ImageNet. ImageNet is more as a small version of ImageNet that can run sufficiently many experiences here on that. We can see actually that Paybo is the blue line. We had also the purple, which is the green line. And we compare always to Spearmint. Spearmint is more the well-known Bayesian optimization framework, which is really always doing from scratch. So Spearmint is not taken into account any kind of human prior knowledge. Paybo and Berkeley are doing that. And we can simply see that on that end here that Paybo achieved a speed of 2.5 on UNet, on ImageNet even a speed of 12.5. So it's really getting faster, and it's getting even to better results at the very end, right? Making use of that kind of expert knowledge which is available on that kind of benchmarks. So we have not defined that. We simply took what is available in the net and what is that kind of image expert knowledge, put it in, it works fluently. Good. So that was all what I wanted to tell you. But I would like also to announce, and I already did with Kevin's group, so Kevin knows that already, but for everyone else, is that I'm very proud to announce today that we will have an automated machine learning conference for the very first time. Oh, there's a typo on the start. It's not 2021, it's 2022. And the website was going online really today. So starting today, you can go to www.automl.cc. And that's really a conference bringing together all kinds of practitioners, researchers, users, of automated machine learning. Why have you done that?
I don't know who did it.
Okay. Impressive. Technology. Yes. So I hope that we see you there. That's co-located with ICML and will be in these days actually. 3 days conference, really bringing together all kinds of people interested in automated machine learning. So that was all. Yes, now it's still on the slide. Thank you, Kevin.
Go back.
Now
I see.
Magic. So if you would like to learn more about automated machine learning, we have a lot of tools actually available really for starter users like others can learn how to PyTorch, really like that's 4 lines of code. You can use that kind of technology. But also, of course, more of these advanced technologies like using Bayesian optimization and so on. You can go to automl.org. You can also follow us at Twitter. You can follow us at GitHub. You can also even follow our YouTube channel if you would like to. Thank you very much.